Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. So we are in the process of trying to get equations to look at a round jet, right? And what we spoke last time was that boundary layer equations, right? They seem to have a lot of similarity to the behavior of fluid in a round jet, right? And therefore we think we can use those equations, right? So what exactly am I talking about there, and what is it that I'm how those equations, boundary layer equations, can be used for a turbulent jet? Let's see. Sounds like interesting, right? So this is where we had stopped last time, right? So we basically said these three things, that in a turbulent round jet, right? So there is a dominant mean flow, actually, because we ignore the z-axis, but the primary velocity was in the x-axis, which is along the axis of the jet. The v velocity was very small. The mean lateral velocity was very small, which is about 1/50th of the center line velocity, right? And also the flow spreads gradually, right? And typically along the x, the rate of change of jet half width is 0.1, right? So which essentially means that the gradients of the quantities, of the mean quantities along the axis, right, is much smaller compared to the lateral gradients, right? And this is kind of similar to what this is. These are the bases, right? This is the basic structure on which we lay down boundary layers as well. Okay. So let's see. So essentially, in boundary layers, so if you do have a boundary layer, right? We've sort of say this is your boundary layer, right? So and this is the velocity. Okay. Now here also, say at some location, right, I take a velocity gradient. Okay. Okay. So right. So of course you can see that the velocity which is within the boundary layer is a function of x, right? It is a function of x, but primarily the change is actually in the y direction. Actually, it changes actually in the y direction, right? So so what I should be tempted to do here is, right, so it depends on x and y, right? And then again we said that the velocity, this profile, right, at say a location like this is only a scaled up version of what it is at this location. So let's say this is say A and this is say B, right? And so the velocity profile at B is simply a scaled up version of the velocity profile at A, because this velocity profile is self-similar, right? We spoke about that. Now, which is also the case. So essentially what that means is that I can pretty much say, so therefore if I need to look at the velocity profile at a particular location, right? And then if I sort of scale it up, I'm going to get the velocity profile at the other location. So when I look at the velocity profile at A, so I'm fixing my x, right? So the variation is therefore predominantly in the y direction. So hence, so therefore I can sort of take that out and I write this in this fashion. This doesn't necessarily mean that it does not change in the x direction. It does change in the x direction, but we use the similarity conditions, and essentially, so we are saying that the velocity is predominantly, there is one component of velocity again here which is predominant, right? So which is the x component of velocity, which is this, which is u, right? So the velocity component, this is the predominant velocity component. This is for a boundary layer, right? I am talking about a boundary layer over a flat plate. So let me just write that. So this is a boundary layer over a flat plate, okay? And it's also a laminar boundary layer over a flat plate. This is quite interesting, right? And so this is predominant velocity component, right? And the velocity primarily varies in the y direction, okay? And the velocities and the velocity profile is self-similar. The velocity profile is self-similar, right? So that's what we are essentially, talking about. That's a description of the boundary layer, right, in over a flat plate. Now this predominant velocity component u, right, it does change along the x-axis, but like I said, it's self-similar. So as long as I evaluate the variation of that at a location, it's only a scaled up version at another location. So this primary change in this velocity component comes in the y direction. So the variation is predominantly, see, this is the predominant velocity component, and its variation is predominant in the y direction, or essentially in a direction which is perpendicular to the flat plate, okay, or to the x-axis. However, you might want to consider it. Okay, so actually, I should basically say this is the y direction. Okay, this is the velocity. These are the velocity. This is the velocity profile. Okay, and this is actually a flat plate, so you might as well just something like that. Okay, right. So this is so that's pretty much what we know about a boundary layer, right? And essentially for these reasons, now we think that we can actually use the equations which we developed, which we have for the boundary layer over a flat plate. Now, those of you who are not familiar with this, so essentially you take the Navier-Stokes equation, right, and you apply it to a boundary layer and develop that equation specifically for a flow like this, right, which is the flow over a flat plate, boundary layer flow over a flat plate, right? And we get sufficiently, we get equations which are definitely less complicated than the Navier-Stokes equations numerically. Numerical equations are much less complicated. So let's just put it that way. Now, you can find, I will write out the equations in a bit and you will see what they mean. Now, but you can take a look at any standard book should give you the derivation of that, like how you change how you take into account the way we are taking into account turbulence, by taking a mean component of velocity and a fluctuating component of velocity into the velocity that is in the momentum equations, mass momentum energy equations. We do the same thing in this case also, right, where again we use all these concepts of velocity being profile being self-similar and things like that, and it being the velocity being predominant in one direction, this variation being predominant in the direction perpendicular to it, the velocity being self-similar. We put all of these ideas into the Navier-Stokes equation and write out those equations, sort of reform those equations to work for a boundary layer, right? So which is similar to what we are doing now also for a turbulent flow. And now I think that if you don't look at the picture here, right, but just look at the definitions, but if you just look at the definition of this boundary layer, it doesn't seem very different from how a turbulent flow is either in a round jet, right? So there also we do have in a round jet also, what are we talking about in a round jet? Okay, that's a bit exaggerated, but what have you. Okay, so here also right, you can take that right, and then you have a velocity profile. Right. So this is what is essentially, which maybe I should draw that here as well. This is the velocity which comes in. This is the velocity profile which comes in. Right. And then once it's exit, this is the exit, right, the exit of the nozzle, right. So then you have a flow which is happening over here, right, and we have called this as U jet. So there is a developmental length which is this dia, right. So beyond 25 times d, right, is when we are looking at the looking at the jet properties, right, which are self-similar. We also saw that the Reynolds stresses are also self-similar, right, beyond the developmental length. So here too, again, we do have a velocity, right. So we have a u naught, that's how we were defining. We have a u naught, right, and then we have a jet spread, right, which is how long does the jet spread at any x. So this is an x which I am, say, defining somewhere from here. This is an x, right. So this x is actually more than 25d, right. So at some location, say x1 actually, okay. So now, yeah, what I mean by is that actually maybe I shouldn't write that there. Okay, so now this x, right, so I am going to write it here, that here the x is greater than 25d. Okay, so this is beyond the developmental length. Now here, so again you have a dominant central line velocity, you have a spread. So how much is that, it starts out from here, right, how much is it spreading over here, right? It is spreading, we know, right, and so this is a dominant velocity which is u naught, right, and this is the spread. So if you look at that, so this is the spread, and then if you look here, So further down you will have something like this, right. Now, so what it, I mean how, so this is the, then this is defined as essentially, right, and you can see that this also is changing as we go along x, right. So this is the jet spread, right, jet half width, which is r half, right. So which is, again you could compare that with the boundary layer thickness, because what we have here, right. So this is the boundary layer thickness, right, and you can see that, so this boundary layer thickness, okay, so this is also dependent on x. So r half is also dependent on x, right. So those are the kind of similarities that we sort of see here, okay, see between the round jet and the boundary layer over a flat plate, okay. All right. So based on that, we are looking at the possibility of using, therefore, boundary layer equations over a flat plate, right. So now, so I think I've kind of sort of described everything. This I can, okay. So let me write it down. I'll just jot this down. Whatever we just spoke, might as well just write this down, right? So so we use the boundary layer equations instead of the full Navier-Stokes equation. So use of boundary layer equations instead of full Navier-Stokes equations, based on what, right? So which is what we just sort of discussed elaborately. So it is statistically, yeah, well, (2D) and, well, I can say x, or essentially is the, I mean you can take your axis system the way you want, but when I say x, I basically mean the axis and the direction of flow, direction of the incoming free stream, let us put it that way, okay. So statistically 2D, x being the dominant direction of flow. So that is what I mean. So I mean this whole x. So it is to 2D. So because this is time variant, right. So if you take stock, look at this, or you take mean values, etc., over a period of time, you will see that the variations are such that x is the dominant direction of flow, and the changes in the flow in the y direction is quite small, quite negligible, and therefore we sort of consider this as a 2D thing, being the dominant direction of flow. Okay. Again, this is also something we've written. Now you make this difference. So the dominant component of velocity is u. Dominant component of velocity is u, but the variation of this is in the y direction, in a direction perpendicular to it. Okay. So this is, I am talking about the round jet now. So gradients of mean quantities predominant in the y direction, right. So essentially in a direction which is perpendicular to the direction of flow, right. So I repeat myself. So the dominant velocity, right, dominant velocity is u. Dominant velocity is the x component of velocity, right, but the variation, but its variation, right, is in the y direction. This is very important, and that's exactly what's going on in a boundary layer as well. Okay. Well, statistics do not vary in the z direction, or I'm not getting into that. So, statistics do not vary in the z direction. So, essentially we are trying to look at how the jet will behave in several locations along the z axis. Well, statistics, like I said, it doesn't behave, we are not getting in, we are not even talking about this. So, I am going to kind of ignore, let us just say we ignore it. Okay. So, which essentially means that this is 0 and the velocities to be considered are, so u and v, right. Yeah, and I think one thing that I thought I should point out. So, now when I say delta, here is the boundary layer thickness, right, and jet half width is r half. It basically means what? So, the boundary layer, where you have a profile, right. So, here within the boundary layer, right, the velocity is not same. The velocity, incoming velocity was u infinity, like this, right, profile, and now what happens is it becomes 0 at the wall here, at the plate, and then it slowly increases itself, and it there's a profile, and then it reaches u infinity. So therefore, this total height over which this entire gradient is happening is your boundary layer thickness. So, similarly, when I say spread here, spread in of the the jet. So, basically I am looking at these velocities, and as we saw in the last class, there is a v component of velocity in the y direction, and at one point it goes and becomes 0, and then it turns inwards, causing entrainment. So, that is what we think is the edge. So, here we demarcate this edge, right. So, here also the spread is not like infinite or something, it is just that it also reaches up to a height of r half, right. And so this is also like how far is this jet. So, if you look at this picture, actually frankly, if you look at say these two profiles, and if you look at these two profiles, you have a velocity profile, you have a velocity profile, you have a height, right, and then there are variations along x and y, and these two are again, the mean velocity profile is again self similar. Okay. So, therefore, there is a lot of similarity, at least on the face of it, between the flow in a round jet and the boundary layer over a flat plate, and that is why we are sort of thinking on these lines, right. So, now so okay, so we reach u infinity. So, here also the cutoff is basically, so as we had said earlier time. So, here there was no flow, I mean this was quiescent, right, meaning there is no flow happening. So, now when the jet comes out, however, there is flow. So, where do we stop? Where do we say that the jet is not spreading anymore? Well, this is essentially a region where the velocity is such that it is quiescent, it reaches that. So, that is how we define what r half is, right. Okay. So, having said that, so again in a boundary layer over here, so inside the boundary layer, this laminar flow, etc., the in layers happening because of the viscosity. The viscosity component is it is viscous, right, but outside of the boundary layer, outside of this blue line, that a demarcation that I have done, it is 0. Okay. Or yeah, I mean, I'm not comfortable writing this thing is 0. Let's just say that viscous nature is negligible. Gamma is a physical property of the fluid, so it cannot just suddenly become 0. Okay, it's just that the viscous nature is negligible, and here it's not inside the boundary layer. So similarly, in the turbulent flow, also within the turbulent jet, of course there is turbulence, but when it's outside of that, right, outside of our half, so to speak, it is quiescent, and turbulent behavior is not there. You can represent your flow there, it's quiescent, but you can basically say in a sense that density can be just rho, right, whereas here it's a rho plus, rho is equal to rho bar plus rho dash, which is a mean quantity and a fluctuating component. So that sort of a definition is not required when you go beyond the jet half width, right, because the flow is quiescent there. So which is again similar behavior to the boundary layer. But it's interesting because here we are considering turbulence, right? In this case, we're considering turbulence. Here we're looking at viscous nature. Okay. So, okay, I should write that as well, I guess. So let me just write that there. So upper boundary should. Okay, so this is upper boundary, that is, yeah, so well, we kind of say it's tending to infinity, right, is quiescent, right, which is essentially meaning non-turbulent, free stream. Okay. All right. Now, having sort of done that, let's just define the following. Okay. So, the following is defined. Okay. Now, there is so we define a characteristic flow width. Okay. So, characteristic flow width, now you call that jet half width, or you call it delta for that matter. So, delta is essentially the boundary layer thickness. So, it's just a characteristic flow width. Okay. So, given any flow, I have a characteristic flow width, which is say delta x. Okay. Characteristic convective velocity. Right, which is, I'm going to call that as this, okay, and the characteristic velocity difference, right, velocity difference between velocity there and the ambient, okay. So, this is characteristic velocity difference in the sense that this is the convective velocity, right, say u here, right. So, the difference between the velocity difference between say a location somewhere here and here. So, think about that. What is you can see, you can basically see graphically, right. This is your velocity difference. Right. Then if you take this location and take this location, right, then this is your velocity difference. So, this is your US, right? What if you then take, so similarly, so you can basically take two locations, so you can take these two, right? This is the velocity difference, right? And what if I take one just below, one just up? What is the velocity difference? Almost zero, right? So that is the convective velocity, and this is the velocity difference. Velocity difference. So when they're almost same, so therefore it becomes zero. Right. So that's what we mean. So similarly, we will use that same sort of thing over here. Okay. So that's what we understand by that. Now, this is very interesting that now we'll have several examples of turbulent flow. So let us just look at that. Okay. So based on this actually. Okay, so now let's just look at this. Okay. Okay, and you have sort of flow coming in, right? Okay, and this is something we've just sort of done. Okay, so this is a boundary layer. Okay, so this is y. Okay, so let's just say I have this. Okay, now so we'll take some location here. Some location here, right? And this of course is the delta, right? This of course is the delta. Now if I were to basically look at, so this is it, and we just spoke about that. Okay. Now, if I were to sort of draw a similar picture for this one, okay, for the turbulent jet. So let's say at some location, so say some location here, right? Again, this x, right, which is, I'm not going to congest that. You know what the d is, right? It's the exit diameter. So this thing here. Exit diameter. Okay. So at some x, right? So if I draw the picture of that, so at say this one. Okay. So let me do one thing. Let me just simply remove this now. Okay. Let me remove this. See if it still makes sense to me. Okay. Okay. So at some location, right? Say I have, so this the spread in this y direction is say delta, right? And I have a convective velocity, right? And the velocity difference, So if I were to write this, the convective velocity, right, is equal to the difference in velocity. Would that make sense? What is the difference in velocity here? What is the difference in velocity? I have a certain velocity, right? And what is the difference in velocity, and why am I saying the convective velocity is equal to velocity difference? So think about it. Think about it. If I, like I said, if you're coming at the edge of here, right? So that's all it is spreading, right? That's all it is spreading. So it's not spreading further. So, you have a mean quantity of velocity. So, essentially now I am going to write this, right, and I am going to say this is u mean. This is a mean quantity, right, and then I am saying that at some in a distance which is a characteristic flow width. So, it could be r half for that matter in this particular case. So, you have a convective velocity which is equal to the difference in velocity, right. What does that mean? Right. So, that basically this is all the velocity, this is the maximum velocity which it has, right, that is the maximum spread, right. So, that is the convective velocity, and right. So, I mean and the flow outside is quiescent in the sense that here, okay, I guess I should write that here. So, then u infinity, right, is equal to 0. It makes sense. So, u infinity is 0, right, and when you come, so say just think that you are approaching the jet from the quiescent flow, right. So, you are approaching the jet jet from the quiescent flow, which is the ambient. So, now if you come from there, initially your velocity is 0. When do you know that you have actually accessed the jet? When you get a velocity c, when you see this velocity, right. So, convective velocity. So, therefore, but the velocity here is 0, right. So, therefore, the difference is exactly that, it is u c minus 0. So, which is the velocity difference. So, therefore, the velocity difference is the same as the convective velocity, that is the maximum velocity or the velocity that you have here, okay, at the edge of the spread. Okay. So, that is what I mean. So, this one is essentially, this is a plane jet, right, this is a plane jet. I will do a few, this is what we are actually concentrating on, and so yeah, this is what we are studying in detail, but it is nice to look at other profiles as well. So, what other forms could it be? Okay. So, this is one case, this is the case that we are looking at. Okay. So, this is the plane jet. Okay. All right. So, then I have another case here like this. Okay. And then I have this, right, and then I have a velocity profile. Okay. Yeah, right. So, I have something which is like basically I am looking at two turbulent jets, right. So, this is almost like, just think about a jet of the kind of pictures we looked at earlier, jet of say dirty water, one jet coming into the ocean, and there is yet one more which is right next to it, right. So, then this becomes like a mixing layer, right, these two will mix, right. So, now we are trying to understand, I mean, how will that work? Okay. So, in that case, so let us just say, so we are going to do there will be an axis system. So, again, right, I do an axis system, right. Okay. That, right, this is my x essentially, right. So, how do we sort of define this? How do we sort of look at this? Okay. So, now this. Okay. Now, convective velocity, right, the convective velocity is, right, so you have a convective velocity. Okay. So, we basically what? Adding up, right. So, then I look at this. Okay. That, and then you understand what I am trying to do here. Okay. Okay, let's just say, let's draw it differently. Okay, how I draw it will depend on. Okay, so let's just say that the velocity. So now we are looking at the velocity of this jet, which is the smaller jet. Okay, so let's just say the velocity is somewhere like this. Okay, so this distance is, so along x basically is my u mean, right? This is my u mean. Let's erase that. Okay, so u mean is what we are looking at. Okay, or let this be here. Okay, let this be the x that we spoke about, and I'm going to draw this again on this line, right? And this is my u mean. I think that's fine, right? So that is fine. Okay. So we are basically plotting, the u mean across y along x axis. So u mean is along x axis. Okay. So now, so along this is going to give me the value of the convective velocity, isn't it? So let's just say this one. Now it has a smaller u mean. So say that velocity is like this. So that velocity is like this actually. Let's just say this, right. So this is my convective velocity, is that right? But the moment I come here, right, I also have this, right, I also have this. So then I have another, so this velocity component is now going to be added, right. So it's going to be added. So then I have something like another component of velocity here, something like this, right. So then I can actually say, so therefore if I were to now sort of draw a velocity profile of this. Okay, let's just draw a velocity profile of this, right. I have one velocity here, so now these two are going to now form one flow. I have two mixing zones. So then let's just say that this is going to look something like this, something like that. Okay, so in that case, so I'm going to say, right, this is the velocity difference. So as you can see, that is also going to change. So as you can see, as I move along x, right, this, both the jets are going to decay. So this is also going to decay, right. So therefore us and uc both are functions of x, right. So it will look something like this essentially. Okay, and then I can take, so essentially what I'm, so I'm basically now forming, it's a mixing layer, right, and I can actually take, I'm taking the center line through the upper jet and the center line through the bottom jet, right, and I can call this as the characteristic length. You see why we said characteristic flow width delta. So we are calling this as delta because for our case here, in the first case, the plane jet, it becomes the jet half width. But if you have a case like this one where you have two, it's actually a plane mixing layer. It's a, right, it's a it's a plain mixing layer, right? So you get a picture like that. Okay. So quickly, I will also just do this, and then it'll be time to stop. So okay, let's just see. Okay. So right. So this is a flow which is coming in. Okay. Again, right, and this is O. Okay. So then right. Okay. So let's just say, so what is this? Well, this is this is a plane wake. Okay. So then in this case, right, so at some location, so say here, okay, so that this is the okay, this is my characteristic height, okay, and this is my convective velocity, right? And what should be the difference? The difference is, well, we just have to write here, there should be some difference. So there is some difference in the velocity. Let's just say it is this, right? So I'm just representing that. So this is essentially the plane wake. So I basically have given you examples. I've basically, I've given you examples where I can use the round jet, round jet in more than one ways, right, with a definition like this, which is similar to which is a similar description of the flow happening over a boundary layer, right, and we should be able to, the idea is that we should be able to solve equations, for specific examples like this. Okay, that is essentially the example. So now I think what we will do in the next class is essentially look at the equations. Now straight away now we will go to the equations, right, continuity momentum equations, and these are equations which are boundary layer equations, but we will write them down using mean components, because now we are going to use those equations which are so what I'm not going to do is derive the boundary layer equations. Okay, like I said, so you could look up another course of mine which is Introduction to Boundary Layers, where I have done that, right, or there must be other courses online as well as standard textbook, Schlichting's textbook, and you can look at that. So I'm going to straight away take the boundary layer equations, right, which are defined from the Navier-Stokes, and then use it for this turbulent cases now. Okay, and when I do that, essentially what I'm going to do is introduce the mean components of velocity, because as you see here that I'm basically looking at the mean components, right. So that's what we will do. So I think yeah, so plane jet is what you should be looking at. I was just trying to give you a couple of more examples. Okay, so all right, so that's what we'll start doing next class. Okay, so I think I will stop here and take it up in the next class. Okay, thank you.